Hello and welcome to our sequence of videos on hypothesis testing. In this video, we're going to talk about the Kruskal-Wallis test. A Kruskal-Wallis test is performed when we want to compare the distributions of two or more independent groups. It is a non-parametric equivalent of the one-way ANOVA. It attempts to determine if there are any statistically significant differences between these groups. What are the key assumptions involved in a Kruskal-Wallis test? It assumes the samples to have been collected randomly and independence of the samples. So the groups that we are trying to compare are supposed to be independent. The observations within the group, again, are supposed to be independent of each other. A different assumption here is related to the shape of the distributions. So Kruskal-Wallis assumes that the distributions we are comparing have comparable shapes. Let's dive into a problem to understand this a little better. In the IT industry, various programming languages are used for developing software applications. An organization wants to compare the performance of different programming languages for comparable projects. The organization has collected data from several development teams who have used different programming languages for their projects. They have generated a score using key performance metrics such as the code execution time, memory usage, and number of bugs encountered during the development process. Using the data provided, conduct a test at 5% level of significance. So let's have a look at the data. How does it look like? All right, so here is our data. So these are the three programming languages. We've not given the names, but we've marked them as P1, P2, and P3. And you can see we have different number of observations for each programming language. So it is not mandatory for Kruskal-Wallis to have equal sample size. For the first programming language, we seem to have 7 observations. For the second programming language, we have 10 observations or 10 scores. And for the third programming language, we have 8 observations. So now that we've seen the data, let's try to put together what all information has been provided. So first is it is clear that we are going to perform this test at 5% level of significance. It is given in the problem. Second is, how do we state this hypothesis? So it's very similar to ANOVA if you've seen. The null hypothesis is there is no significant difference in the performance of different programming languages. And the alternative hypothesis is that at least one programming language is different from the rest in terms of performance. Notice that ANOVA compares the means, whereas in case of Kruskal-Wallis test, we are going to compare the sum of ranks. Let's have a look at the test statistic. Well, it looks a little daunting, but it is a lot easier compared to the kind of test statistics that we have seen so far. It will be very easy for you to compute. Let's just understand the terms involved. So this test statistic is denoted by the symbol H, and we have certain terms here. For example, this uppercase N represents the total number of observations that we have, adding all three groups. This Ri is representing the sum of ranks for the ith group. And this Ni, N subscript I, represents the number of observations for the ith group. Once we obtain the test statistic, we are going to compare it with a critical value from a distribution known as the chi-square distribution. Now, here is how a chi-square distribution looks like. It's a distribution which is characterized by the degrees of freedom. In our case, we'll obtain the degrees of freedom by subtracting 1 from the number of groups that we have. But just wanted to show you a general property of a chi-square distribution, that first of all, it is a non-negative distribution. It never attains a negative value. It can be 0 or above. And as we continue to increase the degrees of freedom, you can see that the chi-square distribution tends to become more and more symmetrical and bell-shaped. Degrees of freedom 5 indicates it's a right-skewed distribution. 10 indicates still a right-skewed, but you can see it's even now at degrees of freedom 20, it's a bit right-skewed, but you can see it's attaining more and more symmetry. Let's now understand the step-by-step process of calculating the test statistic. First of all, we have to combine all the groups and rank the observations in ascending order of magnitude. All the ties to be assigned the average rank. In this case, if we encounter any ties in terms of the values, we will assign them average ranks. We have seen this in the previous videos. Let's do this. So we already have the groups combined, and all we have to do is that we have to compute the ranks. But instead of doing it manually this time, because I've already shown it to you in the last couple of videos, I'm directly going to use the Excel formula for this, which is rank average. It requires the value that we are giving a rank to. It requires a complete reference range, which is all the values, and we should fix it by putting a $sign, and then we can choose 1 here because we are doing an ascending rank. So you can see the first observation from programming language 1 has got a rank of 19. Now, if I just double click on this, this gives a rank to everything. And since the field next to it already contains the formulae, To calculate the rank total, we already have the R1, R2, and R3 values available here. So now all we need to do is we need to bring the formula which guides us how to calculate the test statistic, and we have all the ingredients that we need. So if we quickly look at the formula here, we'll have to do this calculation in a few pieces. Let's just do this, right? So let's calculate the R square, Ri square by Ni values everywhere, right? So for the first group, this is the R1, and we have to square it, and we have to then divide it by N1, which is 7, right? Similarly, for the second group, we have the R2, and we have to square it, and we have to divide it by N2. And the third piece is we have to go to the R3 and multiply it with itself and divide it by N3. Now, in this formula, we are requiring a sum of these three values. So we can, of course, quickly do a sum. So here's the sum. So now we have this value. Now we have to multiply it with 12 divided by n multiplied by n plus 1. So 12 divided by 25 multiplied by 26, this value comes to. So once we have this value computed and this value computed, we just need to multiply these two. Let's multiply this with this, and you get 90.02. From this, we need to subtract 3 multiplied by n plus 1. So what is this 3 multiplied by n plus 1? 3, and the value of n is 25 in our case, so n plus 1 will be 26. This is 78. Let's do this. The difference between the two values here is our calculations. This is approximately 12.02. This is our test statistic H. Now, if this is the test statistic, can we check the critical value from the chi-square table and compare the two? Let's do that. Here is the chi-square table that we are looking at. And how many degrees of freedom are we going to look at? The number of groups minus 1. So we had 3 groups. We'll be looking at 3 minus 1. That is 2 degrees of freedom. The degrees of freedom are listed here, and the area from the right of the distribution is given here. So we are looking for the 5% area under the curve. So wherever we find that it's 5% area under the curve and 2 degrees of freedom, that's the critical value that we are looking at. Essentially, that's 5.99 or close to 6. Now, if our critical value is 6 and the test statistic is approximately 12, here is how it would look like visually. The critical value is here, and to the right is the rejection region, and our test statistic is falling in the rejection region. So which means we can reject the null hypothesis. At least one of the programming languages has a score which is different compared to the rest of the programming languages. This would be our conclusion. Now let's see how do we quickly perform this test in Python. So in Python, once again, we'll be needing the library called pandas to be able to read the data as we had. We'll be needing the specific class from the scipy library to be able to perform this test. Let me call the libraries, and then we are just reading the data. We storing it by the name of data frame. This was the name of our file. The raw data is available in sheet 1, so we're just reading that. Notice that our sample sizes were not equal, 7, 10, and 8. So we'll have to give a specific input for the NaN policy. We are saying ignore the NaN values and do the computations. So when we run this, so we get a test statistic which is not identical to what we manually computed, but it's pretty close. We calculated this as 12.02 and this is 12.05. The p-value, however, is 0.002, which is much less than 0.05. So in both the cases, if we compare the critical value with the test statistic, the critical value is close to 6. This leads to rejection of the null hypothesis, and p-value being less than alpha also leads to the rejection of null hypothesis. So the end result is one and the same. Hope you got clarity on how to perform a Kruskal-Wallis test. Thank you.